questions that you have on the 1-5 homework. This is something you'll have on, of course, your next quiz. There were some graphs there that were somewhat challenging, and I'm hoping that on Monday we can just talk about the 1-6 homework because we're finishing that today. All right, so what do you think? What do you have? What questions do you have about 1-5? Yes, Gloria? 25? Well, actually, I just put this on from the alpha just to help with the graphing here. Let's look at this. This graph right here. So we know we have vertical asymptotes when that denominator is 0. That's going to happen when the sine of x is -1, and that happens at 3 pi halves, doesn't it? And then add 2 or subtract 2 pi to multiples of 2 pi to that, and you get other ones. So here's 3 pi halves right here. Now, and if you rotate in a negative direction, negative pi halves, then you see there's another asymptote. So essentially what you need to focus on is what does this thing look like, but pick a pair of asymptotes. What does it look like between there? And the question we're asked is, this is 1.5, number 25, y is 1/1 plus sine x. So, let me just refresh my memory on what they asked. Locate the discontinuities and illustrate by graphing. So, essentially what you would do is you would say discontinuities exactly at the vertical asymptotes when 1 plus sine x is 0. In other words, when sine x is -1, and that would imply x would be 3 pi halves plus and minus 2k pi. I guess if you're going to want to list all vertical asymptotes, you can add and subtract integer where k is an integer, where k is an element of the integers, and yeah. So integer multiples of 2 pi. All right, so they're the discontinuities, which also are, in this case, vertical asymptotes. Sometimes the discontinuity will be a cut or a jump or an open hole, but here it's just the asymptotes. That's where it would be undefined. Now, now I've graphed it myself, and mine came out looking like this. If you notice, look at the numerator, it's always positive, and the denominator, now it can be 0 at the vertical asymptotes, but it can't ever be negative because the least the sine of x can be is -1. Add 1 to it, now you've got something positive, you know, as long as it's not 0. So you don't need anything down here. It's never, the y is never going to be negative. The interesting thing is to look at it at its edges. Right here we have what I would call an edge where it's undefined. So what's happening close to 3 pi halves? All right, close to 3 pi halves, you're down here. If you're approaching 3 pi halves from below, then you're in quadrant 3. Well, in quadrant 3, the sine of x is negative, right? And when you, let's see, it's approaching -1. The sine of x is approaching -1 in quadrant 3. let's say the sine of x was negative 0.9. All right, you add it to 1. You have something positive, but it's a tiny increment. In fact, the closer you get to 3 pi halves, and this is quadrant 3 right here. The closer you get to 3 pi halves in quadrant 3, then the smaller, in a positive way, your increment will be. Well, it's 1 over a small increment, so that means you're flipping that fraction, so that means it's exploding, it's going to infinity. And the same thing happens in quadrant 4 right here as you get close to that vertical asymptote. You have 1 plus, again, the sine of x is, you start at negative 1 in quadrant, on that quadrantial angle at 3 pi halves. Then then the sine starts increasing to where it's 0 at 2 pi. So going from negative 1 to 0. So when you have those tiny increments, again, the sign would be like negative 0.9 or something like that. 1 plus that, positive 1/10, take the reciprocal, 10. So you can convince yourself that that kind of thing is happening when you draw the picture. Okay. So I think that kind of says what we need to say about it. Locate the discontinuities and illustrate. Now, I did do a little investigation here. Got 1.4 pi, so that's close to 1.5 pi, which is 3 pi halves, right? And saw that the y value was 20. Yes, Gloria?
So if you asked us to draw, did you want us to just draw one asymptote, or as you did?
You need the curve like between two. If you get two asymptotes and see what's going on in there, then these trig functions are going to be repetitive, and so that would be enough. But the truth is, it's not that I don't think you can do this, but on a quiz or test, our time is so limited that I probably would not ask you one like this. I would ask, I certainly might ask you a graph, but probably not one like this. It could be a trig function though, where you're looking in between asymptotes. Okay. But on homework, I feel like this is fair game. We need to practice on things a little harder. All right, what else in section 1.5? Anybody? Yes, Stacey.
29, please.
29. Okay, 29 gives us a piecewise function. F of x is x squared if x is less than 1, and it's the square root of x if x is greater than or equal to 1. Show that this is continuous on all the reals. Now they use negative infinity to positive infinity. Sorry, I'll typically just write real numbers. Either one is fine. Okay, now it's piecewise, so let's examine these two pieces. Are root functions continuous on their domain? Yes, we had a theorem that said that. This says x is greater than or equal to 1, so we don't have any problems with the square root, do we? So on all this domain, it is continuous individually. And the first line is a polynomial. Polynomials are continuous everywhere. So individually, these are each continuous. So, we only need to investigate the situation when f changes from one line to the other, i.e. when x is 1. Because when we're just following one or the other parts of the rule, we've got continuity. Okay, so, and you might even say polynomial, continuous everywhere. And then you might point to this and say root function, continuous when x is greater than or equal to 1. It's actually continuous when x is greater than or equal to 0, but it's only defined on this part of it, so either one of those you could say. Okay, so F, I wonder if I should just draw it. See, the only thing we have to check is see if this connects. When x is 1, 1 squared is 1. When x is, when x is equal to 1, we're following the second line, aren't we? And the square root of 1 is 1. Now, it would have had an open circle at x equals 1 following this first rule. But there, it also is the point 1, 1. So I'm going to graph it so I can talk about it without sounding ridiculous. So that'll be my goal anyway. So all right. So the root function is good for x greater than or equal to 1. So I'm going to do the second line first. The square root of 1 is 1. The square root of 1, 2, 3, 4 is 2. The square root of 9 is 3. So we have this. And this is a filled-in dot. Now, follow x squared. That is true when x is less than 1. So if x is negative 2, you're going to square it and get 1, 2, 3, 4. If x is negative 1, you're going to square it and get 1. If x is 0, you're going to square it and get 0. So far we have our parabola coming in like this. And then all the way up to x equals 1, we're still following the parabola, and we would do an open circle here. However, it was filled in by the second line. So because of this point, since this point is the same following either rule, this is continuous. Now, I'm writing too much because I'm trying to explain this. If I ask you this question, here's what I would expect. I would expect you to say, the first function is continuous on its domain. The second function is continuous on its domain. They happen to connect exactly at the point 1, 1. So there are no holes in this function. Therefore, it's continuous. Something like that would be fine. You know? Oh, okay. Stacy, was that you? Does it make sense? Mm-hmm. Yeah. Okay. What else? Any other questions? Mm-hmm. Yes, Jacob?
So it would be a close on, that's where the square root of x started, right?
That's exactly right. It got the closed, that is closed. It looks like I've drawn it open, doesn't it? It's because it's shiny or something. Does that look closed now? Yeah, it's a closed point strictly because of the second line where x is greater than or equal to 1, yes.
So if it didn't move there, it would be open.
Yes. If let's say we had the second line as it is, but this first, say the parabola was x squared minus 1. So it came in here, and then I had an open circle here. And then they don't connect, so it is not continuous at x equals 1. Right, right, it jumped discontinuity. Yep. Okay, what else? Yes?
Could you do 33?
Yeah. All right, let's think about that. For what value of the constant c is the function f continuous on all the reals? Well, f of x is, and it's been a piecewise function, cx, cx squared plus 2x if x is less than 2 and x cubed minus cx if x is greater than or equal to 2. All right, first of all, notice that it's defined on all the reals for all x's. We've got one line or another that we're following. Okay, now remember, c is a constant number. It's not another variable. When they use c or k in this book, and usually a and b also, those are going to be constants. They're just not telling us what it is. We're supposed to find what it needs to be, because this would not be continuous for any c you name. We've got to find the one that makes it continuous. Well, okay. Individually, what kind of an animal is this? If I graphed it, if I knew what c was and graphed it, it would be a polynomial, right? Something x squared plus 2x, polynomial. And the second line, x cubed minus cx, another polynomial. They're continuous everywhere, so individually, again, like in the previous example, these two lines are individually continuous. So the only place they have a chance for discontinuity is at x equals 2, where it goes from one rule to another. Okay, so you'd say something like that. These are polynomials which individually are continuous everywhere. What do we need? We need them to be equal when x is 2. We need this, c times 2 squared plus 2 times 2, plugging in 2 to the first line for x, we need that to equal 2 cubed minus c times 2. We're not worried about any other x values because this is the hawk right here when x is 2. Plug in 2 for x and find the c that makes this work. Well, on the left I have 4c plus 4. On the right I have 8 minus 2c. Add 2c to both sides. 6c. Subtract 4 from both sides equals 4. So c is 2/3. So, I mean, when I looked at that problem at first, to tell you the truth, I thought, well, this is hard. You know, how are we going to know what, how are we going to know what that is? And then the answer lay in the fact that we're only concerned about it not being continuous when x is 2. So plug in the 2. and find the C that makes that work. Okay, Brittany? Yeah?
Yes. Could you actually do either finish 41, because you started it yesterday, but I wasn't sure how to finish it, or 35?
Yeah. All right, I'm going to just show you this on 41, Brittany. On 41, we let f of x be cosine x minus x. So that's f of x, so we need to evaluate it at each endpoint, so 0 and 1. F of 0 is 1. F of 1 is negative 46. Now, I wrote this kind of, let me write this all that clear. This number is positive, this number is negative. And 0 lies between positive and negative numbers. It's a continuous function, it can't jump. It can't jump the x-axis when when y is 0, can it? It's got to, someplace between it assuming a positive value and it assuming a negative value, it's got to cross the x-axis forming a 0. So, since f is continuous everywhere, in particular on 0, 1, by intermediate value theorem, there must be a 0 between x equals 0 and x equals 1. Or anyway, in the open interval between 0 and 1. And that's really all you need to do on this one. Get it equal, get everything on the left-hand side, call that function f of x. We want to see if it hits 0 in between there. That's how you do 41. Now, the other one you asked about, I'm going to show you my notes on it too. Yeah, so, yes, Jacob?
Where did that 150? On the last one, 41.
On 41, oh, if you take the cosine of 1, now see, we're in radians, Jacob, right? Okay, the cosine of 1 radian occurs in quadrant 1, and its cosine is, this is a calculator problem. You'd have to use a calculator.
So that, something like that would be on the test then?
I mean, if I put that on the test, I would let x be something where you know the cosine, like 5/6 or something like that. Okay, you're just responsible for those unit circle values that you memorize and treat. Those I think are fair, not the cosine of 1 radian. All right, so I'll put this in the notes, Brittany, but I'm gonna try and go just a little bit through this, not just take too long on it since we've already done a few today. This is 35. All right, so it's a weird one because of that greatest integer function. But it says, all right, we have, first of all, you have this function that works out fine. You have difference of perfect squares. It factors, and we can cancel the x minus 1 divided by itself is 1. So it just collapses to x plus 1 times x squared plus 1. Now, it didn't have a limit out in front of it. So we have to consider the fact that we are saying x can't be 1. It's got a removable discontinuity at a equals 1. It's got an open hole in that graph right there because it's not defined there. See, there's no limit out in front. So this is equal to that times that when x is not 1, and they're asking for us to call it a particular value where there's a discontinuity. in B, that factored 2, took out an x in the numerator and then factored this quadratic. So there was a common factor at x minus 2 in the numerator and denominator. So it went into itself one time. So it factors now as x times x plus 1, just a polynomial. However, it has a problem too. When x is 2, then when x is 2, this makes sense, but the original statement of the function doesn't. So we have to say there's an open hole there at x equals 2 as well. So that's again a removable discontinuity at that one place. So those go okay. Now letter C, it asked us to define. If we wanted to define a certain A value that when we plug it in would force it to be continuous, then that's where you just go to this last expression where everything cancels, put 1 in there, 1 and 1 is 2, 1 squared plus 1 is also 2, 2 times 2 is 4. So plug that missing value you had to punch out into the final canceled form of the equation, of the function, and find what would have made it continuous. And that happened in B also. Remember, we realized there was a problem when x is 2, so it's got a punched out hole. So it says, what could we define x equals 2 to be for the y value so that there's no punched out hole? Well, 2 times 2 plus 1. 2 times 3 is 6. So you take the final canceled, simplified form, plug in x equals the problem here too. See what it would need to be to make a smooth curve. That's how, that's what you can do with things that have removable discontinuities. Could we define it a little bit differently so that it didn't have that hole? Okay, then letter C, that's the one that's sort of tricky. Okay, greatest integer in sine x. Well, the sine of x ranges between -1 and +1 forever. And so the only integers between those, -1, 0, and +1, those are the only values it can assume because it assumes a value of an integer every time. So y is always going to be -1, 0, or +1 in this problem. So here's what's happening. We can't fill something in to make this a continuous function because there's jumps. We could fill in this dot here or something if we redefined it, but we can't do anything about this right here. That's a jump. So it's not going to be continuous no matter what. But if you're thinking about how do we get the graph, what you have to do is, all right, right here between 0 and pi halves, we're in quadrant 1, right? So we're looking at the sine function. The sine of 0 is 0. It rises through quadrant 1 to hit its max at pi halves, right? So the sine is varying from 0 to 1 in quadrant 1. All the time that it's less than 1, the greatest integer function is returning a value of 0 because it takes the integer less than, like the greatest integer in, if there was the number 1/2 in here, it would return the value of 0. It takes the integer to the left of that fraction on the number line. That's what this function does. So all in here we're stuck at 0. However, when we get to pi halves, the greatest integer in the sine of pi halves is exactly 1. So jumps up right there. But once we get into quadrant 2, right away the sine starts getting to be a fraction that's less than 1/2. It's only 1/2 right there at pi halves. Once it's less than 1, the greatest integer function jumps back down, returns a value of 0. So that's why we start out here and 1 just at that dot, and then it's still 0 all the way to x equals pi. All right, now when you're at pi, you're right here, and we're starting to dip into quadrant 3. where the sign of x is negative, isn't it? All right. So remember what the greatest integer function does. It returns a value of an integer to the left of the fraction. So if I have in quadrant 3, let's say the sine of my angle was negative 0.8. It's going to return a value of the integer to the left of that negative 0.8, which is negative 1. That's why it's tracking along right here at a level of negative 1 until it gets to 3 pi halves, and the sine of 3 pi halves is actually negative 1. That's how you have to graph this thing. It's kind of strange, isn't it? Looks like some kind of code. In fact, that'd be kind of a fun code to write something with the greatest integer function in it anyway. I'll put this in the notes so you can kind of look at it if you wish. And let's go in and talk about 1.6. Let me find where we were. Okay, now I wrote down 1.6 continued. I wrote down the limit as x approaches infinity of the square root of x squared plus 1 minus x. Okay. Now, this is, sometimes these limits are things you can just look, and on inspection you can figure out what they are. This is not one of those. And the reason is, we've got something under the radical, even though we're taking the square root, still, as x goes to positive infinity, it's increasing without bound. And so is the minus x, it's increasing without bound. So we have this icky kind of situation of infinity minus infinity. So what does that mean? That's garbage. You see, how do we evaluate that? So we need to do something to this expression to see if there's something that makes more sense in order to evaluate it. Well, okay. So the book suggests we're going to put it over 1 and multiply it by its conjugate. So square root of x squared plus 1 plus x over itself. Not because there's anything wrong with having that radical in the numerator, just because we're searching for another form. And we can multiply by 1 and not change the sense of the problem. Well, if we did that, let's see if it would help. This is just something to try, you guys. All right, using FOIL on the numerator, square root of x squared plus 1 times itself. X squared plus 1. Outer product, x times square root of x squared plus 1. Inner product, negative x times square root of x squared plus 1. They add to 0, don't they? Which is the reason we chose this pattern. Then we have minus x squared. In the denominator, we have that x squared plus 1 plus x. Okay, we do now have a 0 sum in that numerator. So it looks like the limit as x approaches infinity of 1 over the square root of x squared plus 1 plus x. Now, do you see how this denominator with x increasing without bound is much easier to interpret because it has a plus sign between those two. So we've got something arbitrarily large plus another thing arbitrarily large. Okay, so this is going to infinity when we take this limit, and that's staying at 1. 1 over something arbitrarily large is going to 0. Like in our discussion yesterday, I see a skeptical look on your face, Andrew. I'm going to get the picture. Skeptical is good though. so if I remember this, the limit as x goes to infinity of 1 over x, and when I did my t-chart, 1, 10, 100, 1 divided by that, 1/10, 1 over 100, as these are going to infinity, these are going to 0, right? And you know, we have this going on that right hand side. It's going to a height of 0. Okay, that's what's happening to this fraction. It's very similar to that kind of problem. You have denominator getting really big, then you take the reciprocal. Yeah. Okay. Now, here comes some other definitions, not ones that you have to do a proof. But I need to talk about them because they write them in delta epsilon arrays. All right, let's look at this first one. So, if f is defined on an open interval containing a, except perhaps at a, then if you say the limit as x approaches a of f of x, now notice there's no right or left designation there, so we're approaching a from the right and left. We're just a little bit delta away from a on the right and left. If you're going to say that limit equals infinity, then for every value m that's positive, so let's say m, we're going to pick, if m is some y number, pick a height of m. Okay, so there is some a with a delta associated with it, so that if x is within delta of a, that implies f of x is greater than m, is taller than m. So, so whatever a big number means to you, if you want to say something's approaching infinity, say you pick 100,000 or 1,000,000 or whatever big means to you in this particular problem, that's your m. And you want to say, well, could f of x get this tall? Well, yeah, if I get x within a certain increment of that, then f of x will be that high. So it's a delta epsilon definition that kind of goes with finding a vertical asymptote, and that's what this definition is about, finding a vertical asymptote. As x approaches a particular number, y is going to infinity. Finding a vertical asymptote. Okay, in definition 7, this is about finding a horizontal asymptote. So, I drew one that's kind of neat looking, where we've got the amplitude decreasing as we go further to the right. If f is a function defined on some interval, say from a to infinity, then the limit as x approaches positive infinity, so this is right end behavior of f of x is that L. So in other words, this is honing in on a certain height L. If for every epsilon that you pick, there is, so in other words, pick a certain height away from that line L of L height. Okay, so pick that. Well then, can you find an n over here so that when you do anything past f of n to the right, you will be less than epsilon away from L. Same kind of definition about finding a horizontal asymptote, it would look like that. So notice that this is limit as x goes to positive infinity. This thing does not appear to approach L on the left, does it? Positive infinity is just talking about the right end. How far do we have to go out to get this function to be within this band, within epsilon of our desired height, L? Okay, then one more. Here, definition 8, one more definition, and we'll do some examples. Yeah. So if f is defined on an interval from a to infinity, so this time, let's say this is A here. Then, as x approaches infinity, so right end, the height of it is getting large without bound. So all polynomials do this. They either go up without bound or down without bound on the right. They don't have horizontal asymptotes do that, polynomials. Are you rowdy? Okay, good. So for every m greater than 0, so say we pick this particular height, there is an n greater than 0, so that if you pick an x that's farther to the right than n, f of that number will be higher than m. So that's how you would use delta and epsilon to define it in this way. Again, you do not have to use these definitions for any proofs, but still, this is how we make this idea specific, and we need that in calculus. Okay. Now, let's suppose that we looked at y equals the sine of x. And we were looking to see if we could find a horizontal asymptote here. Well, here's the thing. Yes, it oscillates around the line y equals 0, doesn't it? But here's the thing. I can't pick something that's far enough along the line down here so that f of that particular x value will get within an epsilon that's as small as I want. Because you can pick any positive increment epsilon. Let's say I decided to pick epsilon equal to 0.01. I wanted to get that far away from 0 because I'm claiming I've got a horizontal asymptote over here. Well, see, it's still going to go up to +1 and down to -1, no matter how far along to the right I go. So the end behavior of this, it does not have a horizontal asymptote. It continues to go up as high as to 1 and down to -1. It's got, that amplitude has got to decrease as you go along for there to be a horizontal asymptote. Nod your head if you're with me on this. Yeah? Oh, good. Okay, then let's look at y equals x cubed. Of course, this is a polynomial. And if we looked at the right end behavior, we're taking something arbitrarily large and cubing it. It's going to be arbitrarily large, isn't it? It's increasing without bound, so I can make this limit statement. If I wanted the left end behavior, I'm taking something negative and cubing it. It stays negative, but it gets arbitrarily large as I go along in this direction. So this, I can say, equals negative infinity. It is getting large without bound in a negative way. And I don't need to give a right or left designation here because whether I'm approaching 0 from the right or left, both of these are going to a height of 0, aren't they? So I could make this statement that limit exists. Okay, so there's just one other example I want to do. This is example 10 in your book. And if I had something like this, the limit, you're still evaluating limits. This is our last section of limits of x squared minus x. This kind of falls in the category of that other limit that I showed you where it doesn't make sense to say something arbitrarily large minus something arbitrarily large. So you really can't make that argument, even though, yes, as you go to the right, x squared is increasing faster than x, isn't it? You want to say this is infinity, but the minus sign is problematic. We need to explain a little bit better. So here's a good way to deal with this one. If you just do one step, the limit as x approaches infinity of x times x minus 1, isn't that true? Now from this perspective, I've got something arbitrarily large and positive times another thing arbitrarily large and positive. So it's times. So two large things increasing without bound, and you multiply them. Now you can argue that that would be infinity, that increases without bound. Now, some of you are gonna come to me, I know this, and say, well, if x is positive, which it is, we're looking at the right end, and I know what that's a polynomial. And x squared on the far right end is bigger than x. So I know that this is gonna increase without bound, the right side of it is gonna go up. You know, you've also learned that thing in pre-cal where you say, well, a polynomial is dominated by its highest power term, right? Its leading term. And the leading term here is x squared. Its coefficient is 1. That's positive. So this is going to go up to positive infinity. That is true. That is true. But this is kind of a nice way of writing it so that you can see clearly. Arbitrarily large and positive times arbitrarily large and positive. Okay. So, all right, now Rowdy's going to talk to you about PASS and maybe about SI also, is that right? Okay, come on down.
So I'm going to pass out some bookmarks. On the back of these bookmarks, there's a QR code to download the QR code reader or scanner on your phone or whatever. You can get all of the past hours where Calculus 1 is offered. It's most days. I think it's Monday through Thursday, like 12 to 10 or something like that. Anyway, so I am a PASS tutor in the PASS Tutoring Center. My hours are Tuesday from 12 to 4 and Wednesday from 12 to 3. And then you can come there and we'll help you out with your homework, whatever. And I also I'm also a supplemental instructor. Does anybody know what supplemental instructor is? Have y'all heard of that from other classes?
Yes, and they feel slighted because they don't have
Yeah.
one.
Yeah, we're a little short-handed this semester, and I actually sit in on another class, another professor's class, but we go over roughly the same material, so I should be able to help y'all out if y'all come to my sessions. I don't have any bookmarks for SI, but I can write my session times on the board if you don't mind. Okay.
No problem.
I write my session times on the board, and I also write the supplemental instructor UT Tyler website, and then I'll have my times, and then Conrad is the other supplemental instructor, and he has times as well. Right?
Whose class do you attend?
Dr. Bearden.
Okay.
But y'all can go to any of my sessions or Conrad's sessions or any variation of them. We have to follow the same guidelines. Our like reiteration style might be a little different, but y'all have any questions before I write stuff down? Good? Okay. I'm also going to give you all my email address. Y'all feel free to email me about any questions you have. And I also have office hours there today from 12 to 1 in the PASS Tutoring Center. Did everybody get a bookmark? All right, and like I said, if y'all have any questions, feel free to email me. I also do the Remind app, and if you want to get involved in that, you can just email me and I'll send you the link, okay?
Okay, thank you, Rowdy.
You're welcome.
Okay, so that's what I wanted to talk about today, and I usually keep you a little bit too long, so I'll hang around and for another 5 minutes if you would like to go over any other questions, and otherwise I will look forward to seeing you on Monday. Oh.